Yeah, I just introduce our speaker. Dr. Shyam Sundar Pasunurthi received bachelor's degree from Jawaharlal Nehru Technological University, Anantapur, and master's from IIT Kanpur, and PhD from University of New South Wales, South Sydney, Australia. During his PhD, his research involved development of new combustion models and their applications to high pressure direct injection diesel combustion in ICE engines. Currently, he's an engineering manager in Simerics, India, where his area of focus is on advanced numerical flow and thermal analysis, including CFD optimization and new method development, covering different automotive systems and fluid power systems. So this is about our first speaker, Dr. Shyam Sundar Pasunurthi, and I will introduce our next speaker, Dr. Madan Kumar P, lead engineering Simerics. He specializes in computational fluid dynamics simulation across wide range of engineering application, including gearbox and bearings, lubrication, rotating machines, and flow-induced acoustics. He earned his doctoral degree from IIT Madras and subsequently pursued postdoctoral research in France and Canada before joining Simerics. Dr. Madan has extensive hands-on expertise in high-fidelity CFD simulation in industrial CAE application. At Simerics, he works on advanced simulation technologies for automotive and engineering applications with focus on lubrications, oil flow, thermal management, and complex transient multi-phase systems using multi-purpose CFD tool that is Simerics MP+. His tasks include customer support, technical consulting, pre-sales demo, training new engineers, and performing benchmark studies to showcase software accuracy. So with this brief introduction of both the speakers, now I hand over the session to Dr. Shyam Sundar to proceed over the presentation. Over to Dr. Shyam Sundar, sir.
Yeah, thank you, Sagar, for nice introduction. Good afternoon, all. Let me share my screen. Sagar, are you able to see my screen and all?
Yes, we can.
Yeah. So the topic of discussion for today is on e-drive simulation, preferably on oil-cooled high-power density e-drive units simulation. In that, covering from advanced lubrication to thermal management and challenges and solutions through Simerics MP+. So I'm Shyam Sundar, and my colleague Madan also will share some part of the presentation. So moving forward, this is my outline of presentation. So in introduction, I covered main features of high power density e-drive units, and following with some more introduction covering what are the silent features, and also the cooling technologies that are involved for this kind of high power density e-drive units, specifically for electric vehicles. Then what are flow and thermal analysis that needed to be done to understand the current design and improve the designs. So during that process, what are the simulation challenges that we face? Mainly three different kinds of simulation challenges that we face, and that also I cover. And so ultimately, what kind of solutions, CFD solutions, Simerics MP+ provides for those challenges. So at the end, I'll show our published CFD results and analyze those results using different analysis, CFD analysis results. At the end, my colleague Madan will show live demo of using two different tools from Simerics MD Plus. Okay, with that, at the end, we'll take Q&A session, Q&A, and we can end the session. So moving forward, yeah. So yeah, as I mentioned, I'm going to cover, yeah, electric motors are around us almost from century old, and entire the technology is known through us. But the electric vehicles, the electric drive units that are meant for electric vehicles are definitely they are high power density. Nowadays, has a as 25 kilowatts per kilograms of weight of e-motor. The technology is going up to that point. Now, whatever we see in the market, they are up to 7 to 10 kilowatts per kilograms of e-motor, which translates to around 200 to 300 HP. So that power of that much level of high power density e-motors are needed for nowadays vehicle motion applications, especially for cars and high-end high power vehicles. So during that process, what happens is that high heat generation happens that need to be dissipated efficiently. So that's why for the same reason, this kind of electric drive units are oil cooled. Oil cooled. They are direct oil cooled. They are not indirectly contact kind of thing. They are directly oil cooled. And this high speed, the high power density motors, directly the speed would be in the order of 15,000 to 20,000 rpm. So integrated gearbox also comes with that, which helps in reducing the speed of the output speed to needed vehicle speed. In turn, actually increases the high torque, which is needed for the right motion of the vehicle. So the advantages would be, obvious advantages would be zero emissions on the road, high transmission efficiency, which is in the order of 90%, easy controllability, either speed or torque, easy controllability would be there. Of course, less breakdown would be there, especially with respect to the electric drive units. Of course, there would be breakdowns with respect to batteries around on different components of electric vehicles, but we are not going into that. We are purely going to concentrate on electric drive unit and CFD related challenges and solutions related to that. So then next, what are different cooling technologies? As I mentioned that these are oil cooled, direct contact oil cooled. So as oil that we are going to use, that usually used is a dielectric oil, which is a back conductor for electricity. So in that case, it can be directly poured into different heat source components and can be effectively taken out the heat. So then what are different oil cooling strategies are there? So if you look at a typical electric drive unit, it consists of as I'm showing you here on right side, the center rotor, and for over that stationary stator. State. So the rotor, it has magnets. So it is usually cooled by sending oil from the center of the shaft. Because of its rotation, the centrifugal effects are created, and it is spilled over different what is a component, especially the magnets it is spilled over. So that is the centrifugal action. Remaining some fraction of oil from the rotor is also passed on to the stator. This is the stator actually. So, and stator cooling, mostly it happens there are windings, stator windings. Usually this kind of high power density electric drive units consist of hairpin windings, which are tightly packed to get high power output. So in that kind of situation, it results in high heat generation. So there are two kinds of cooling technologies that are usually followed. So direct contact cooling, which the oil coming from the stator directly pour either in the form of jets with high velocity jets. It is poured over the exposed windings. There are two exposed on the either side of, this is the off a domain on the either side of the exposed winding that is directly poured. And there is a jacket cooling. This windings pass from one side to the other from the center portion. Actually, they pass. That is also cooled by jacket cooling. So then over that, and the gear set and bearings also exist as part of the entire train unit. Those bearings and gears need to be lubricated by the same oil. So by the phenomena called splashing, as the gas rotate, the splashing phenomena happens. Okay, let me play this animation. Splashing phenomena happens, and also direct spray jets, like we do here, spray kind of cooling over the windings. Over the gas, also spray jets are used to lubricate them properly. Okay, so during this process, what kind of different fluent thermal analysis are needed to understand the design. So for this, I segregated into three different kinds of analysis. The first is lubrication, lubrication of gas set and bearings. So it actually okay, we need more amount of oil to lubricate entire gas and bearings. But at the same time, if you add more amount of oil, it will lead to more spill loss. So there would be a balance between these two. We want to reduce the spill loss. At the same time, we want to have adequate lubrication. So these two factors are influenced by the speed of the rotor, oil temperature, which reduces the viscosity and reduces the spill loss. At the same time, it can easily, with increase of temperature, which I mean, and at the same time, it can easily splash over. At the same time, and one more factor which can influence is sump oil level. Sump oil, more is the sump oil level, more the gas need to pass over that, it will lead to the spill loss. And the cooling performance, there are three different sources of heat sources: copper losses to the electrical electricity pass over the windings, and iron losses to the both, it happens to the, in the stator and rotor, due to the varying magnetic field. And other losses would be because of the windage effect of the oil, and the mechanical losses. These are very less compared to the copper losses and iron losses. So oil, which we are directly pouring over the different components, takes almost 80 to 90% of the heat. So definitely, we need to take care of how efficiently this oil path we design. Okay, so and also targeted cooling of the different components using spray nozzles. So this is a very crucial part which we need to understand from the current design and improve upon that. So moving forward, so yeah, and another one, last one is pump and aeration. For this kind of high power density pumps, usually a PD pump, positive displacement pump, is used. Here I'm showing a G rotor pump. So, and this kind of entire vehicle undergoes a different kind of drive cycle. During that process, what happens is that acceleration and deceleration happens, and it can, lot of splashing of oil can happen. So with that, the pump which picks up oil from the sump can get exposed. That is called as pickup tube, which I'm showing in the bottom animation. You see the pickup tube, that inlet to the pump, can get exposed to air and leads to a lot of aeration, and reduces the oil delivery performance of the pump, and in turn the less amount of oil will be will be pumped to different components to cool the different rotor and stator components, and also to lubricate. So this need to be controlled, and effectively we need to design the positioning of the pickup tube of the pump. So here directly on pump I am showing here to understand, because of the acceleration and deceleration, how pickup tube is exposed. Okay, these are three different kinds of analysis are needed. So in this process, what are the different challenges we face? So definitely, I'm highlighting the challenges that we are going to face for 3D CFD simulation of e-drive unit. Definitely, the geometry for this kind of e-drive units would be very complex and consists of lot of rotating parts in the form of gas, rotor itself, bearing, and also the pump. And importantly, to capture the spill losses and lubrications, intermeshing of the gas need to be captured, which would, the gaps which would be in the order of micron levels. And this is going to be a oil and air kind of mixture. We need to model this one by a two-phase kind of modeling, a multi-phase kind of simulation at high rotating speeds, which actually incur a lot of mass conservation issues between the two phases, and the sharp capturing of the sharp interface between the oil and air. These two become challenge when we want to model oil air to multi-phase simulation. And one more important thing is that when we go to thermal simulation, uh, obviously it needs a complete conjugate heat transfer modeling, which actually when we combine both fluid and solid, because of longer time scales of getting the temperatures to be stabilized, we end up actually simulating longer duration. So to address this kind of simulation, this kind of longer solid time scales, what kind of simulation strategies, thermal simulation strategies, which we need to follow. And adding to all these things, overall runtime would be usually when we go with multi-phase heat transfer simulation, 3D CFD simulation, the runtime would be very high. Whoever is into this kind of simulation, they know very well that how challenging to run this kind of simulations. So then, so I'll go into what kind of Simeric solutions we have for to address all these challenges. Okay. So then, okay, in Simerics to address these challenges, I mentioned about complex geometry and rotating parts. So for this in Simerics, we have customized automated hexaedral mesh generation, which can take care of the motion of gears, and at the same time, as I'm showing in the right side bottom view, it can capture the intermeshing of the gears in the micron level, which is very important to capture the lubrication and the spill loss effects, and the even heat transfer effects that can happen between the gears. And also the pump itself, to capture its performance, we need to capture the leakage gaps and the uh, complete functioning of the pump without approximating any geometrical features of the pump. And coming to the gears, I want to highlight some more features of the gears. In Simerics, we call it as the general gear. So we call them as templates. To highlight more features of the template, general gear mesh template, it can handle any kind of gears, either it is per gear or planter gear system or system of complex series of gears. We don't simplify the geometry, and it captures the all micron level gaps, and at the same time end up building the structure mesh, which is very important to capture the accurate physics, both flow physics and the heat transfer physics, and capture the lubrications as Prashian physics accurately, and which is crucial for spill loss prediction and also heat transfer prediction. So moving forward, here, and one more important thing is that how do we do multi-phase simulation? In Simerics, we have explicit VOF solver, which is fast and accurate in capturing the interface. At the same time, we have adaptive time shifting. In any multi-phase solver, the challenging task would be controlling the CFL number, always keeping it less than 1. For that, we have an adaptive time shift scheme, which automatically takes care of a CFL number. And one more, we have a mixed time scale coupled heat transfer simulation, which can actually give different, which we enables us to maintain different time scales for fluid and solid simulations. And one more importantly, we can actually give anisotropic thermal conductivity properties for laminated solids, either in the stator and the rotor. Because of this, we can achieve faster runtime. Okay, these are the solutions for the three what I said, the challenges from lubrication, thermal analysis, and the aeration. These are the Simeric solutions for this we have. And moving forward, I have some results, safety results, okay, which are published by our engineers. So first, I will start with the cooling performance. In this, okay, by using our well-established coupled heat transfer simulation, we simulated a complete E-motor. Here, drive unit it is not considered, but if we have simulations in which drive units are also considered. So here you see that very nicely captured oil pouring over the stator windings, and after nicely wetting the both exposed windings, and it is collected at the bottom. Pump that is there, a PD pump, which again sends back into the after heat exchanger, it pulls down and sends back into the E motor. So like that, that heat removal process goes on. So this is for the stator, and going into the rotor part. In this particular design, the central portion where magnets exist, that heat is taken by conduction, and it is transferred to the by conduction to the end rings. This is called as end rings. These end rings are cooled by rotating sprays. You see very nicely these are captured. There are two rotating sprays on each side, they take out the heat from the end rings. The conducted heat from the magnets, it is taken to the end rings and cooled by the splash side because of the centrifugal effect. And this is the temperature distribution that we got, and different components. If you see overall casing on the stator casing and the stator windings and the inside rotors, uh, and further moving forward, this is the temperature comparison we got across different thermocouple points that are lying both on the stator and the rotor. Okay. So moving forward, I have another case which is the pump aeration and pump performance. Here, yeah, just let me play this. Here we have test data with which we compared. Here you see that this is the actual e-motor. There is a pump, a G-rotor pump. Because of acceleration, because of the actual drive cycle, the oil that is there in the sump, it is coming to one side. So with time, you see that lot of air bubbles that are going into the high pressure line, they are increasing, and which will reduce the pump delivery performance of the power street displacement pump. So because of that, what would happen actually? So this is another animation which shows an isosurface of oil inside the sump, and also the oil that is going into the high pressure paths to the different locations of the e-motor. You see that with time, you see that almost it is pump is getting exposed. So because of this, we have monitor points. This is the line pressure at one of the main line at the outlet of the pump somewhere in this location. So whenever aeration starts happening, before that line pressure, this is normalized line pressure. Before aeration starts happening, line pressure is very high, very good. When aeration starts happening, that line pressure reduces and remains flat, and then again when it deceleration stops, when the sump oil level comes to the normal level, line pressure recovers and the pump starts delivering normal flow rates. So that we could compare very well with the test data. So this kind of simulations involves the kind of solutions that I highlighted in my previous slides. At the end, I have another spill loss and lubrication paper. In this, okay, this is a drive unit. Separately, we simulated a drive unit in which there are two sets of helical gate drive units along with bearings. Along with this is one set of bearing. This is another set of bearings. This is another set of bearings, and here a lot of gate rings are there. Here, before coupling into the wheels, there is a differential. So yeah, the lubrication of all these components understanding is one more criteria of objective of this simulation, and also the quantify the spill loss that happen at different conditions of operational conditions of this entire drive unit. So here you see below this, I don't have cross section because of confidential agreement that we had with the customer. So I cannot show the internal details of this, but below this, the splashing of oil that because of rotation and because of the sprays that are there, direct to sprays, very nice oil is sprayed over the gears and also directed toward the bearings, internally lubricates. These bearings that we uh, consider the exact relative motions of all the motions of the bearing. Inner race, cage, balls, and the outer race is fixed to the casing. So for all the bearings we did, and also as I mentioned, we captured the intermission. So here you see, here in the right side plot, I'm showing the normalized power loss with change of oil temperature. With increase of oil temperature, usually we expect the spill loss to reduce. That's what we are seeing at different speeds of the pump. You see, we are plotting from 3,000 RPM to almost close to 11,000 RPM. At low temperatures, low temperature, the spill loss is very high, and that increases with increase of low temperature. Viscosity would be high. At the same time, with increase of speed, the splashing effect would increase. With increase of speed, it increases, spill loss increases. The trend would be same with increase of speed. But as the increase of temperature, the spill loss will come down compared to the low temperature cases. That effect we are able to capture. Then one more thing is that effect of level of oil inside this. When the oil high level of oil is there, it will induce high spill losses because whatever the gas that are dipped into the oil, they need to actually counter that oil and take the oil, scoop the oil, and encounter that resistive forces and splash the oil around that. So due to that, the spill losses would be high when the high oil level is there. So that with the decrease of oil level, the spill loss decreased, and with increase of speed, obviously it will increase. The spill loss would increase. So moving forward, uh, yeah. So yeah, these are overall the I covered different features of e-drive unit that are meant for electric vehicle applications and the challenges that are involved, and CFD solutions that we got, and some results addressing those challenges, how we captured and how we evaluated. And these are I want to cover a little bit about our Simerics unique capabilities. So we cater template based approach. Which I mean is that a customized model setup approach, which actually automate, which reduces user intervention considerably, and helps to generate good quality mesh and model setup for different kinds of pumps, valves, vehicles, and different marine applications, which I am showing here. For automotive applications, we cover different vehicle applications, both external and internal kind of application, piston cooling applications, tank filling, sloshing, and general gear, which I mentioned as part of the drive unit, which I covered that. And different pumps, we have different templates, which helps us to set up very fast and go into the simulations very fast. Even for marine applications, we have different templates to take care of that. So because of this, it makes easy for any CFD engineer to set up even complex CFD simulations easy, and also minimizes different CAD operations that are needed. And for example, if we take for vehicle applications, we can take raw CAD, and by using our vehicle template, we can capture different features and remove unwanted mesh by using our advanced seal technology, and get the required mesh with less time, within the 3 or 4 hours. And we can handle, especially we can handle moving mesh and dynamic meshes very easily, which is our strength of our Simerics tool, and also micron level gaps we can handle. And moving forward, a little bit I want to cover about our Simerics company. It was founded in 2006 by engineers and scientists from different computational physics background. They are all PhDs and who started their career in 1980s, and it was started in 2006. They came together and started. And initially, the name was Pumplix. As we expanded our applications into different areas and different multi-purpose kinds of simulations, the name is changed from Pumplix to Simerics MP+. We started with pump kind of applications, then moved into general purpose kind of applications. So now we are calling it as Simerics MP+. In this area also, we have different kinds of catering tools. We have a tool that is linked with CAD applications like Cryo. We call it as CryoFlow. And even with marine applications, we have linked with Rhino. We call it as Rhino FlowRT. Like that, different kinds of CAD linked solvers are also there, mainly to cater for CAD engineers. Simerics Simpliplus is meant for advanced CFD engineers, which is a multi-phase, multi-physics, multi-purpose CFD solver, like any other solver. So we are headquartered in Seattle. We have a branch in Detroit, Germany, and we are from India, located in Bangalore, and we also have a branch in UK. Okay, moving forward, these are some of our selected customers from different kinds of automotive and different kinds of companies, um, uh, pump and different kinds of EV, e-drive units, and big OEMs, automotive OEMs, um, and uh, and these are the customers from Simerics India customers. Yeah. Now we'll move forward. These are Yeah, at this point, my first phase of presentation is done. Before going into a live demo, which my colleague Madan will cover, we want to take up some any question and answers that are there. Or at the end also, just we want 2-3 minutes. We can take some couple of questions and move forward. Yeah. Sagar, do you have any questions of who any from who put in the chat box?
Hello, sir. Hello, sir. Omkar this side.
Yeah, yeah.
So right now there are no any questions. So I
Yeah.
request participants to switch on their camera mic and they can ask their questions. Or else we can take at the end.
Yeah, else at the end also. At the end also is fine. We'll take it up. Okay. And now we'll move forward with the demo session. Yes.
Thank you, Shyam, for the introductory presentation. So, good afternoon, all. Madan here. So, I will take you through the eDrive unit live demo. So, before going into the live demo, I want to explain the model with which we'll be working on the live demo using our CAD tool SMP CAD. So this is the demo model that we'll be working with. So this is a demo of eDrive unit. So it has gearbox side and the e-motor side. On the e-motor side, you can find the important parts like stator and the stator winding. So these the importance of these parts and how the associated heat losses and everything Shyam covered in his presentation. So the important application of any CFD simulation is just to get the temperature prediction and the oil distribution. So whether the oil that they are supplying is able to take away the heat effectively. So to cater that, what we have done is we have created this demo model, including all the cooling channels and bearings, which will be there in the actual model. So it has all the rotor shafts, stator windings, all the critical parts, and also the gerotor pump. Even included the pump so that we can use this model to demonstrate our capability to predict the aeration effect or cavitation effect. On the gearbox side, we have a typical like two-stage gear set. So the shaft that is connected to the e-motor directly is the input gear. From that, we'll be mating with bigger gears to reduce our like the input speed. So you can see this is the intermediate gear, which kind of reduces the speed from let us say 15,000 RPM to like 8,000 RPM. Then it will be coupled to a intermediate pinion, which is hidden here, and the intermediate pinion will mate with the output gear, which is taken out connected to the wheels. So this is a typical e-motor setup. So like Shyam mentioned, the components which contribute to heat loss or heat source critically are the stator and stator windings and rotor and the magnet. So generally, all the e-drive units, they will have exclusive oil channels to cool the stator and its windings, and also the rotor part. Right? In addition to that, on the gearbox side, depending on the application, we'll have a oil sump where it will be like they call it as a dip lubrication. It's predominantly used for low speed gear application. But when we go to high speed applications, like we can see in this e-drive unit, generally people use nozzle injection spray lubrication, which is more directed, and it will not incur that much spin loss like the sump lubrication. So with this, we want to demonstrate how Simerics enables the development of efficient E-drive units within a shorter period of time. So I will show it in demo. So what are the workflow that we have followed and how we can achieve that in a shorter period of time using our CAD tool SMP CAD and our CFD tool Simerics MPP. So before going to the next slide, first I want to briefly explain you the CHT coupled heat transfer simulation workflow. Right? So like all the simulation will start with the CAD because that's the starting point for all the simulation work. So we start with the CAD and whatever the workflow we follow using our CAD tool SMP CAD I have listed here. So generally, if you take any CAD from the customer or any OEM, the CAD they have it will not be like very clean, and it will not be renamed and grouped properly. And especially for a complex model like E-drive units, you may have more than hundreds of bodies or solids. We have seen like 2000 or 1500 solids, which will be like very difficult to work with. So the initial starting point, what we will do is we'll group and rename all the parts accordingly. For example, there will be like 140 or 200 stator winding bodies. So what I have to first do is I will rename everything as stator windings, and then I'll group them accordingly, so that it will be easy for me to work. The model will be easy for me to work with. So this is the initial step. So once that step is done, the next step, whatever we are going ahead with is, in general, the CAD that we'll receive for CFD simulation, it will not be a perfect CAD. It will have a lot of imperfections, especially in terms of gaps or also in terms of overlaps, etc. So generally, first what we will do is in SMP CAD, first we will analyze the gap. So we have an option called gap analysis, where it can loop through and it can capture the gaps of a pair of bodies where they have gaps, right? So that once you identify all the bodies, you can use our gap filling operation, and it will very nicely close all the gaps that are present in our body. So once the gap analysis is done, the another common CAD imperfection that we can very often we come across is the interference, or we can also call it as overlap. So two bodies which are supposed to be separate, it can be overlap. For example, the stator can have some overlap with the rotor, which is in physical, it's not possible, right? So in those kind of cases, what we'll do is similar to gap analysis, we have interference analysis, which will give us the pair of bodies which are overlapping, and we can perform Boolean subtraction operation, which will remove this overlap, and we can get very nice touching kind of body, right? So these operations we are doing so that we can get very nice proper interfaces or conjugate interfaces, which are very critical for our conjugate heat transfer analysis. For example, in the stator windings, where even Shyam highlighted that it contributes more to the heat loss. In stator windings, always it will be covered with a liner material, which is the insulator. If the interface between the stator windings and the liner material is not captured, then the heat transfer between these two components will not be captured correctly. When we are not capturing this heat transfer correctly, then it can give rise to incorrect temperature prediction. So that's why it's always important to capture these interfaces correctly, so that the temperature distribution that we predict from our simulation will be correct, right? So once we do this CAD cleanup operations like the gap filling and the Boolean subtraction, then to ensure that all the interfaces are captured correctly, we do interface analysis. It will list out all the successful and failed interfaces. Once if the model is not able to capture some interfaces, it will give out which two bodies are having these failed interfaces. So we can always go back to their two bodies and we can fix that. Because in where it will be become very important is, for example, in a E-drive unit, you will be dealing with a big CAD with 200 or 2000 solids. And if you have any interface which is failing in any set of pairs, manually or visually finding them is very time consuming, and it will not be always correct. So what we do is, like SMP CAD itself, it will automatically give you the pair of bodies which are missing these interfaces. So you can directly go to part A and part B, and you can fix why that interface is failed. So this is the interface analysis step. After that, what we will be doing is we will extract the fluid volume, because our CAD is clean. So we ensure that the CAD is clean. Then the next step is extracting the fluid volume, and we'll also export the XTL files for meshing. So whatever the workflow that I am showing here is part of our SMP CAD, and it is CAD operations. Once the STL export is done, then we will be moving on to the Simerics MP Plus environment, where we will be setting up the coupled heat transfer simulation. So the first step in the coupled heat transfer simulation is creating the solid mesh. So at this step, we will be having the STL files of solids and the fluid meshes, fluid surfaces. So first we will be creating the solid mesh, and then we'll set up the solid model. So for the solid model setup, we will be providing the heat source conditions and the volume properties. For example, for stator windings, rotor windings, we have to assign copper property. For casing, we have to assign steel properties. Like that, we have to assign the volume conditions and boundary conditions, and we'll finish the solid mesh setup. Then we will start with the fluid mesh setup. So we have the STL surfaces for the fluid mesh also. Here we'll create the mesh, and we'll assign whatever the flow rate conditions we are giving to the oil, and other properties like what is the oil temperature, and we can also like consider properties varying with temperature. Our viscosity, density, everything can be function of temperature as well. So those kind of things we will take care in the fluid mesh and setup. So once the fluid setup is done, what we'll be doing is we'll run that fluid model without any heat simulation. We call this as cold flow simulation, and we do this because we want to like establish the flow field before starting the coupled heat transfer. If our flow field is not established, then even though if you start your heat transfer simulation, your temperature will take very long time to stabilize. To avoid that kind of scenarios, what we always do is first we'll establish the flow field by running the fluid model without any heat. Then we'll move on to the coupled heat transfer simulation. In the next slide, I'll just show how we are taking care of the coupled heat transfer simulation and what we mean by that. Okay. So the reason why we are going into this coupled heat transfer simulation is generally the temperature change that happening in the solid, it takes place at very slower speed compared to the fluid. So if you run both of them together, then the simulation will take very long time for it to stabilize, right? So what we are doing here is, in the coupled heat transfer approach, we are separating out the fluid and solid models separately, and we are just exchanging the boundary conditions in terms of fluid will give out heat flux, where solid will give out temperature. And these temperature and heat flux exchanges will happen in the conjugate interface. So this fluid supplied heat flux will be applied to the solid conjugate interface, and the solid supply temperature will be applied to the fluid conjugate interface. So this is the idea behind the reason behind separating out the like solid and fluid models. So now I can go to the demo, live demo of our SMP CAD. So before going on to that, I'll just briefly tell what are the things I'll be covering in the demo. So first thing I'll be covering is I'll just show how we can group and rename multiple solids in SMP CAD. Analysis. Yeah, and I'll show how we can automatically like clean up a lot of interference or overlap.
Is it from you?
I think, sir, there is an echo.
Yeah, mine is
Yours is muted, right?
Yes.
Yeah. So now you go
Yeah.
ahead once.
Yeah, I think now it is clear.
Yeah, it's fine, sir. Now it's fine.
Yeah.
Yeah, okay. So I'll also show how we can remove the overlap using our interference analysis tool. And also I'll show the extracted fluid volume, how we can extract the fluid volume using our domain operation, so that we don't have to follow the conventional approach where we close the openings and we'll subtract the entire model with a larger bounding volume. That we don't have to follow here. I'll show how we can automatically extract the fluid volume, and also how we can use the leak identification option in SMP CAD to our advantage of finding the leaks, which will be like speeding up our CAD cleanup time. Finally, what I'll do is I'll create the imprinting. I'll perform imprinting, and I'll show the generated conjugate interfaces, which we will be using for the solid heat transfer simulation. So let me go to the SMP CAD. So this is the GUI of SMP CAD. Right. So here we have our demo model. So in SMP CAD, we have an option called entities, where you can find all the bodies here, like what are the bodies here. So in this model, we have a total of 55 bodies. Okay. So the first operation, like what we will be doing is we will be doing the renaming and grouping operations. Like I mentioned here, some bodies, they have the proper naming like gears, end rings, like that. But some portions, they don't have, some parts they don't have any proper naming. They have like generic or random names. So what I will be, what I want to do is, first I'll show you how I can use the rename option to our advantage, so that we can do the renaming and grouping in a single go. First, let me hide the housing. So here I have all my gears and rotor stator windings, etc. So first, let me do this grouping and renaming. To do that, what I have to do is I have to select all the bodies that I want to group and rename them. So whatever the parts that I have selected, it belongs to the liners, which encloses the stator windings. So once I select this, then I go to operation. There is an option called rename body set. So once we click it, I have to add all the selected bodies into this bodies, right? Then I have to give the prefix. Let's say liners, and I want to rename the entire name with liners, and I'll say perform. Okay. So once I perform this operation, you can see the part underscore some random numbers. It made into liners. The reason we do generally these kind of operations is when we want to even in later stages, if I want to assign some certain boundary conditions and volume conditions to liners, I should know where the liners are there. I cannot identify the name part with different random names. So it will be very handy when you want to rename it properly. So it not only renamed, it also created a group called liners. So you can see it created a group with inside which also all the liners are now grouped there. One more thing is I have another part which belongs to the bearings. So what I'll do is I quickly select all of them. I'll go to rename body set. The existing selection I am removing and I am adding the new selection. This I rename it as bearings. So once I perform this, here you can see all the solid underscore some random names, they changed into bearings, and the bearing groups also got automatically generated. So these operations will speed up our CAD cleanup time. Also, this grouping will make our workflow very structured, so that in later stage we will not spend much time and effort in renaming the stuff. Right? So this is the first operation we wanted to show in SMP CAD. The next one is the interference analysis. Interference analysis, for example, I want to understand how good is this CAD is. In reality, most of the CAD will have a lot of imperfections like overlaps or gaps. So to do that, first let me show you the imperfections that we have in this model. To visualize that, I am taking a section view along the explain. Okay, so this is a section view, and if you see in this section, we can very nicely see there is a overlap between this gear body and this gear body, right? And also this body has some overlap with this body. Even these two shafts also have some overlap. These are just for demo purposes. So you can see here there are like clear overlaps, even though, and always it is not very easy to visually like take some sections and find it out when you have multiple bodies. So what we'll be doing here is we'll be using our automated interference analysis option to find out this interference. What I'll be doing is, under operations you can find interference analysis. Okay, and interference analysis, what I have to do is I'll select all the bodies because I want to check all the bodies for interference. Then I'll say intensive search yes. So this will give a interference analysis dialog box. First we have to say analyze. So this analysis, it may take like within a minute for this kind of smaller parts. And if you have 1,000 bodies or more than that, depending on the number of bodies, it can go like 20 minutes or 30 minutes also. Because it has to like analyze the possible combination between each bodies and what are the interference it gaps. So it will list out all the interferences, all the like if you are doing gap analysis, all the gaps, and individually I can check what are the places where the interference is. That also it will give, and I can decide whether I can manually do it or automatically like subtract everything to remove that overlap. So these operations will come in handy when you are working with very big models, and you cannot always like practically feasible for you to spend much time in doing it manually. So this interference analysis, now it has done this analysis and it has given 4 interference, right? So what it is giving is, first there is a interference between intermediate gear and intermediate pinion gear. So I can click here. So it will take us to the like interfering gaps, so that we can directly like understand where the interference is happening. So you can see here it took it to that overlapping gear part in these 55 bodies. And if I'm new to this CAD model, where I don't know like where the interference is happening, so these things will be very much helpful, so that I can find it like each and every parts, like what are the interference it happens. So you can see here the intermediate gear has some overlap with this shaft. So like this, I can go on and check all the parts. So what I am going to do now is I'm going to use Boolean subtraction, which subtract all operation. So here it will subtract the smaller body from the larger body. It means the material is removed from the larger body. So let me do subtract all. Yeah, so you can see all the status is success. So let us go and go back and check our CAD. Yeah. So now you can check the CAD. The material from this gear is removed, which is the larger body, and but now they don't have any overlaps. They have very proper interface. So this is one of the operation we wanted to demonstrate, which will like show how fast we can do CAD cleanup operations in SMP CAD. So now quickly I'll show how we can extract the fluid volume. So to extract the fluid volume, the general conventional way what we'll do is we identify all the openings we have in the CAD model, and we'll manually close them. And then we have to like create a bounding box, and we have to subtract these bodies from that, so that we can get the trapped fluid volume. But that will be very much time consuming, especially when you have a lot of bodies. So the automatic operation what we will be using is domain operation. Let me show that how we are doing that. So in Simerics, we have operation called domain. Domain in the sense it will extract the fluid domain for you. So I have to set Boolean based operation to no, and I am considering all the entities for this operation. So first thing I have to select is the openings. So what I have to do is I just have to select all the openings, the visible openings that I can see in this model. So even the pump also I am selecting. Okay. And then I have to give the seed phases. Seed phases is just like to tell this SMP CAD like whether it is internal fluid volume or external fluid volume. I just have to like select one phase internally and set it as seed phase. So once I have finished this operation, so what I will be doing is I have to click on the find operation. So like I said, we can also find the leakages. So I can click leakage find operation. So it will help us to find in case if there is any leakage with the model, it will help us to identify it and fix it. So now the leakage identification process is going on. It will take a minute or something to show it up. Yeah. So the leakage identification is done. So what we can do is we can just adjust the position just to see if there is any leakage is happening in the system or not. Generally, if you go to maximum like 0.9 or something, the fluid volume that you should be seeing is there should not be any fluid volume leaking into the solid model. So here we can see very nicely it is captured, and we don't see any the green part, which is the fluid volume, is leaking into the casing. So once I ensure that, I'll just click on create. So when we click create this one, it will automatically extract the fluid volume, and it will create another entity under this body section, which will be named as domain. So that domain will be our fluid volume. In case if you want to split rotating or stationary volumes, all those things, we can perform those operations in this extracted fluid volume. Yeah. So now we can see the number of bodies present in the entities increased to 56, and we can see the domain is created here. Let me only show the domain. Yeah. So we can see here this is the extracted fluid volume. It very nicely extracted all the pipings and all the gears and everything. You can see even the pickup tube and everything. It very nicely extracted. To show how complex it is there inside, let me create a section. Yeah. So here we can see all the gears intermeshing and all the channel, rotor channel and stator channel parts, bearing, and everything is captured in a single go. We didn't spend much time in doing all this manual work and stuff to get this feed volume. So this is the same workflow we follow with all our other customers as well. We follow this typical workflow, typical operations to speed up our setup time. So let us say like the fluid volume extraction is done now. So what I will be quickly showing is I want to show the imprinting process, how we can get the imprinted STL. Let me close this one. So since we have ensured our CAD is clean and everything, I will be showing, I want to show the solid to solid imprinting, because in coupled heat transfer, we don't need the imprinting between solid and fluid domain. So I will not include my fluid domain for the imprinting process. So what I will be doing is I'm selecting all the bodies without the fluid volume. Then under operations, you have a option called tessellation. So under tessellation, you can say user defined, because I don't want to include the domain, and add the selection. And here you can see the perform imprinting is set to yes. So this is the important thing. So now it will automatically identify the interfaces between solid to solid parts, and it will very nicely separate that during the tessellation process. Let us perform the tessellation. Even the tessellation process also, it depends on the your CAD model. For example, if it is very big CAD model, like if you have 1000 and 1500 bodies like that, it may take closer to half an hour or 45 minutes for this tessellation process. Since we have only 56 bodies, it will be done under a minute, so it will be pretty fast. Once the tessellation is done, we can very quickly manually check what are the interfaces it captured, and if we are satisfied with the interfaces it captured from this tessellation process, then we can move on to the case setup. Like we can start the mesh and everything. So here it created all the CAD surfaces. Let me display the CAD surfaces. So this is a tessellated model. Okay, I can display grid on this. So you can see it's not a CAD body. It's a STL file. It's a tessellated body. So in this tessellated body, under Simerics convention, what we have is, when I say bearings 13 underscore shaft, then it is a interface. Whenever you see a slash, it means interface. So this is interface between bearing 13 body and the shaft body. Likewise, this is interface between rotor body and the end-ring body. So let me like highlight only these interfaces just to show that what are the interfaces we have captured over. The main tricky thing in this kind of simulations are the liner and the stator interfaces, because they have generally like very thin gap, and capturing them is very critical. And here you can see it captured all the
Can we move to models?
yeah. So these are the interfaces. Especially I wanted to show the liner and stator. So these are the interfaces it captured between the stator windings and the liners. Since we don't have enough time, I'll quickly show on our model setup, like how we.
Yeah, this is the final step.
Yes.
After that, we'll import
Yeah.
into.
Once
Simerics
once we are done with the tessellation, we'll move on to the mesh, right? So here I have a like already ran model with the e-motor side. We have only motor side here, and this is the fluid volume. So what we can see here is, you can see there will be a gap. So this is the extracted fluid volume, and the solid is separated here. Okay, the connection how we are doing for the coupled heat transfer is, all other flow and heat simulations are same, but we have a module in Simerics called data exchange. The job of data exchange is just to like exchange the boundary conditions like wall heat flux and the heat wall temperature between the fluid and stator side. For example, if you take this stator wall, so this stator wall under fluid volume, we assign it as mixed scale coupling. So it is a coupled boundary then. So automatically it will taken as coupled temperature. So this will receive temperature from the heat source as well in the solid model. In the same model, if I go to this solid model, you can see this is the solid corresponding solid interface for that model. Here you can see same, this is a coupled boundary, but it will receive heat transfer coefficient from the fluid model. So like that, this exchange will happen. And like we mentioned earlier, these simulations, coupled heat transfer simulations, we start after the cold flow simulation. So here what we do is, we have ran till here we have run cold flow simulation. Once we ensure that the flow is stabilized in the system, then we switch on the coupled heat transfer simulation. And the main area of interest here is the, like I mentioned, is the temperature distribution of the solids. So mainly like the heat sources like the stator and stator windings, everything. We will like we can monitor using the plots. We can create thermocouple points, and we can monitor them. We can also like plot like volume average temperatures. For example, if I want to get volume average temperature of my stator, I can plot this, and I can see that if the temperature is stabilized, I will stop the simulation. So these are the one important things that we look into this simulation. And in the fluid model, we always like interested in the air like oil flow path. So here we can see how the oil is very nicely pouring from the coolant channel onto the stator windings, which are the critical heat source in this model. So you can see how the oil distribution is captured, and if there are any hot spots, or if the cooling is not sufficient, then from this CFD simulation we'll come to know where we can improve, whether the cooling channel or cooling flow path we have to optimize. So those kind of design directions we can get from this simulation. Also, we can get other critical information related to the solid models and its temperature distribution from the solid model side. The, like we highlighted earlier, the critical one major advantage of this coupled heat transfer approach is, we'll get all these temperature stabilized results within a shorter period of time, since we are like separated them and using this coupled approach. If we run it together, it may take pretty longer time to stabilize.
So the mesh count of fluid is in the order of
Yes, yes.
around, for this demo model,
So
it is
one more,
10 million.
yeah, it is 7.6.
10 points, and whereas solid is around 15 million.
Yes. So if you look at the mesh count for fluid, it is around 7.6 million, and solid it is 5 million.
Oh, 5 million.
And for this kind of simulations, even we can go afford to go very high cell count for the solids, because we are not interested in the history evolution of temperature. We are just interested in the stabilized temperature. So we can run it steady state. So like Shyam mentioned earlier, they can have different time scales. The fluid can be with a transient and finite time step. Solid can be either coarser time step or it can be also
Steady state
steady
simulation.
state simulation.
If you are simulating drive cycle, then we'll go for transfer simulation of solid.
Yes. Yeah. So with this, we want to like conclude our live demo, and we are open to questions. So if you have any questions, we'll be like happy to answer your queries.
Thank you, sir. Thank you, Madan sir, and thank you, Shyam sir, for insightful session. Now I request the participants, you can open your mics and you can ask your question, or else you can drop your questions in chat box.